Late one afternoon in 1979, a fully loaded DC-10 lifts off from Chicago. Then, seconds later, the entire left engine rips away, tearing vital systems from the wing. In just 31 seconds, 273 lives are lost. Was this a freak accident, or the result of an invisible flaw hiding in plain sight? The answer to how did this happen begins deep inside the aircraft's metal frame. The DC-10's left engine hangs beneath the wing, not held by simple bolts, but mounted through a complex structure called the pylon. This pylon acts as the bridge between the engine and the wing, channeling every ounce of thrust and weight into the heart of the aircraft's frame. At its core are two sets of attach fittings, forward and aft lugs, each designed to absorb enormous forces during takeoff, landing, and flight. The forward lugs, shaped like thick metal forks, extend down from the pylon and slot precisely into matching clevises on the wing's front spar. These lugs are over 1 inch thick and anchored by massive 1.75-inch titanium bolts, and they grip the wing with a strength measured in tens of thousands of pounds. Behind them, the aft lugs handle the lion's share of the engine's forward pull. Each is even thicker, built to bear the brunt of thrust, up to 150,000 pounds at takeoff, transferring energy from the engine directly into the wing's rear spar. Inside the pylon, a maze of hydraulic lines, electrical wiring, and fuel conduits snake from the wing into the engine, all routed through this narrow corridor. Any disruption here risks not just the loss of power, but the severing of critical systems that the wing and flight controls depend on. The load path is carefully orchestrated. The aft lugs absorb most of the thrust, the forward lugs steady the engine against vertical and twisting forces, and the pylon beam itself ties the entire assembly together. This design leaves little room for error. If any part of the pylon's attachment is weakened, even by a hairline crack, the entire structure is at risk. The pylon is more than a mounting bracket, it is a lifeline connecting the engine to the wing, and through it, the fate of the aircraft is decided. As the engine and pylon assembly ripped away from the left wing, the violence of the break left more than an empty mount behind. Nearly 3 feet of the wing's leading edge tore free in the same instant, exposing interior structure to the slipstream and leaving a jagged wound that ran inboard from the original pylon attach point. The aluminum skin and underlying ribs, designed to channel airflow smoothly over the wing, were twisted and ruptured. Hydraulic lines routed through that section burst open, dumping fluid and pressure in seconds. Bundles of electrical wiring, once shielded inside the pylon fairing, snapped and recoiled, and connections to cockpit systems were severed without warning. The damage went deeper than the eye could see. Hydraulic fluid, essential for operating the wing's leading-edge slats, bled out onto the wing and into the airstream. The outboard slats on the left wing depended on that pressure to stay extended during takeoff. With the lines torn and pressure lost, the mechanical locks that held the slats out became vulnerable. At the same time, electrical circuits for warning systems and engine monitoring were cut, silencing indicators that might have alerted the crew to a hidden configuration change. Photographs taken after the crash show the left wing's leading edge missing a section about 1 meter wide, its interior structure splayed open. The break mapped a direct path from the point of pylon separation through the heart of the systems that kept the wing's lift devices deployed. In the chaos of those seconds, the aircraft lost not just thrust, but the integrity of its wing and the silent safeguards built into its design. Leading-edge slats are movable panels along the front of an aircraft's wing. On takeoff, they extend forward and reshape the wing's profile to create more lift at lower speeds. The DC-10's slats are powered and locked in place by hydraulic pressure, and without that pressure, the slats can lose their grip and slide back into the wing under aerodynamic force. When Flight 191's left engine and pylon tore away, the violence of the separation ruptured hydraulic lines running through the wing's leading edge. System pressure dropped instantly, and the outboard slats on the left wing, those farthest from the fuselage, lost the force that kept them extended. As the aircraft climbed away from the runway, the left wing's outboard slats, now unpowered and unlocked, retracted on their own. This happened silently, with no cockpit warning. The right wing's slats remained extended, still held by undamaged hydraulics. The result was a hidden split in wing geometry, one side configured for maximum lift, the other suddenly cleaner and less forgiving at low speeds. The stall speed for the left wing jumped higher, while the right wings remained safely low. The loss of hydraulic pressure had done more than retract a few panels. It had quietly turned the left wing into a trap, waiting to snap shut as the aircraft tried to climb away. This mechanical chain reaction, set off in seconds, created an invisible iron balance. The aircraft's controls, instruments, and checklists all assumed both wings were still configured the same way, but with the left outboard slats now retracted, the margin for safe flight had narrowed to a razor's edge. Inside the cockpit, the flight crew faced a situation that was far more complex than a simple engine failure. Standard procedures for a DC-10 losing an engine during takeoff are clear. Maintain takeoff power on the remaining engines, pitch for the target climb speed, and follow the engine out profile drilled into every pilot's memory. But the instruments and warnings the crew depended on had been gutted by the violence of the separation. The number 1 engine gauges, EPR, N1, N2, and oil pressure, went blank in an instant. The slat disagreement light, designed to alert the crew if the wing high lift devices were not where they should be, never lit up. The stall warning system tied to the left wing, including the stick shaker, was dead, its wiring severed along with the hydraulic lines in the shattered wing root. What remained looked deceptively normal for a left engine failure. The flight instruments, attitude, airspeed, and altitude were all alive. The right and tail engine gauges read as expected. The climb speed, V2, was set for a standard engine-out scenario, under the assumption that both wings still had their slats extended. But the left wing outboard slats had silently retracted, raising the stall speed on that side far above what the crew could know. No warning horn, no flashing light, no tactile cue broke through the routine. The only evidence was hidden in the aerodynamics, not in the cockpit. The flight engineer and pilots worked through their checklists, responding as training dictated. With no external clues and no time to analyze a subtle, invisible change in wing configuration, the crew was left flying blind to the real danger. Their focus remained on keeping the aircraft climbing and controlling asymmetry, unaware that the margin for safe flight had already vanished. In those critical seconds, the information gap became fatal, not through error or neglect, but through the simple absence of any warning that the left wing was now primed to stall first. American Airlines maintenance logs from Tulsa, March 1979. Document a critical departure from manufacturer instructions. Instead of separating the DC-1010 engine from its pylon before removal, mechanics used a forklift to support and lower the entire assembly as one unit. This shortcut, meant to save nearly 200 hours of labor, introduced risks the original procedure avoided. During a midnight shift, workers removed the aft pylon bolt first, leaving the engine and pylon pivoting on the forward fitting. The assembly sat overnight, supported only by the forklift. As hydraulic pressure bled off, the forks crept down, shifting the heavy structure out of alignment. When the day shift resumed, the pylon had jammed against the wing clevis. Mechanics repositioned the forklift and forced the fit, unknowingly gouging and bending the upper flange of the aft bulkhead. No non-destructive testing followed before reinstallation. The damage, invisible beneath paint and fillets, would go undetected until it failed in flight. In a quiet laboratory, the fractured remains of the DC-10's Pylon bulkhead told their story under a microscope. Metallurgists examined the upper flange and found a crack stretching nearly 10 inches, its surface lined with fine fatigue striations. Each microscopic band marked a single pressurization cycle. By counting these striations, investigators traced the crack's slow advance through 374 flights, the exact number logged since the Tulsa maintenance. The match was undeniable. What looked like a sudden structural failure was, in fact, the final act of a flaw that had been growing cycle by cycle for weeks. This scientific evidence confirmed that the damage began during the forklift-assisted removal and reinstallation, not from a manufacturing defect or random overload. The metal itself preserved the timeline, linking the hidden crack directly to the catastrophic separation on takeoff. Today, every commercial jet's critical systems, mounts, wiring, and hydraulics are scrutinized with lessons written in the aftermath of Flight 191. But as aircraft grow more complex and maintenance pressures persist, safety depends not just on design, but on vigilance. In aviation, the smallest oversight can become tomorrow's catastrophe. Stay curious and stay vigilant.